So there are many quantities and applications that we've dealt with previously that are defined by magnitudes. For instance, if we were to refer to something as 45 pounds, 45 is a magnitude because it's a quantity, it's an amount of something. Or perhaps we're talking about a magnitude of 50 miles per hour. That's a speed, so that's a quantity, that's a magnitude. So oftentimes we refer to those as scalars. Those are real numbers. But a lot of applications involve a different type of quantity referred to as a vector or a vector quantity. And vector quantities don't only have a magnitude, but they also have a direction. So for instance, if I were to refer to a car driving 50 miles per hour, that would be referred to as a scalar. But if I said that the car was driving 50 miles per hour east, now I recognize that that is a vector, because vectors have both a magnitude and a direction. So vectors are going to be drawn as rays or lines with an arrow pointing in the direction of travel, while the length of the vector is going to be referred to by its magnitude. So here are a few different representations of vectors. This first vector right here describes a vector of 10 pounds being pulled or pushed at an angle of 30 degrees. So this is basically like a force. Okay, if I were to be pulling or pushing with a force of 10 pounds at an angle of 30 degrees, then this would be one particular type of vector. This is another vector that begins at O, ends at P, but I'd like you to realize that the direction of the arrow or the length of the arrow doesn't show where it begins and ends. It shows essentially the length of that vector shows how strong the force is. So if the force was, let's say, this amount, that wouldn't mean that I started pushing here and ended pushing here. That would just mean that I didn't apply as much force as the blue one, but it was still moving in the same direction. So we refer to this as vector OP, or in other words, vector U. Now, a lot of times in textbooks, you're going to see vectors written in bold letters. The problem is we don't have the ability to write in bold, or rather, I suppose we do, but it just takes a lot more time to write in bold, and it's a little unclear what we're referring to. So instead, in physics and in calculus, when we deal with vectors, the way that we deal with vectors would be that we put a little arrow tip over the vector. And we could see that OP is the same as vector U, but again, we would put a little arrow tip up above U. And this is important to see the difference between a vector variable and a scalar variable. If I just had the vector U, then that would imply that we had, or if I had the vector U, then I would have an arrow tip over it. But if I had the scalar U, now that would just be some scalar quantity like 5 or -7. And this next one, we could see that this is referred to as PO, as the vector PO. And the reason is because it has its initial point at P and its terminal point at O. So the way that we would write that would be vector A or vector PO. So in general, when you are graphing vectors, what we would typically do is that if I were to label this vector, then I should see that this is my initial point here, and this is my terminal point. And if we were to define this by or label this as a particular vector, we would label this as, say, vector V. Okay, and the length of that vector, okay, this length is referred to as the magnitude of V, and the magnitude or the length has its own notation, which we will be putting inside of bars. So if we put our vector V as the vector itself, the magnitude of vector V is our scalar. Now, vectors can be equal if they have the same exact magnitude and the same exact direction. So for instance, in the diagram to the left, we see that vector A is in fact equal to vector B. Even if they are listed, let's say that we're looking at these on an X and Y plane, even if they're drawn in different places on the graph, they're actually the exact same vector because they're pushing with the same exact force in the same exact direction at the same exact angle, and therefore we refer to those two vectors as being equal. We could also see that C and D would be equal vectors here. But now let's take a look at, let's say, vector A and vector E. We can see that both of those vectors have the same magnitude, but they're not equal because their directions are different. So notice that vector A would not be equal to vector E, even though they have the same magnitude. What we can say, however, is that the magnitude of vector A is equal to the magnitude of vector E. Now we could also see that if we were to look at vector A and vector F, notice that F is in fact pointing in the same direction, pointing at the same angle with respect to the X and Y axis. But because they're different lengths, they are also not equal. So we know that vector A is not equal to vector F. But what we're going to see shortly is that vector F is a scalar multiple of vector A. So they are in fact going in the same direction. It's just that vector F might be a certain percentage or a certain fraction of what A actually is. In order to see what we mean in more detail, let's just take a look at vector U. Okay. So vector U is pointing up to the right, and it would have a certain angle, and shortly we're going to get to the point of how we describe the direction of that vector. But notice that this is vector U, and because I could actually stack two of those vector U's in the same direction on top of each other, then I see that this is referred to as 2 times vector U, or 2U. So it's a scalar multiple of vector U. If I look at 3/2 U, that just means that I can put the entire vector, vector U, and then I could take half of that and stack it onto there in order to get 1/2 of vector U. You could see that the green one here is half the length of vector U. So the way that we're going to draw these vectors is to make sure that we're drawing them parallel to their original counterpart here. But we just need to realize that the scalar multiple tells you how many times to add those vectors together, or basically how many of those vectors forms that new vector. Now I'd like you to take a look at these two vectors, vector 2U and vector -2U. Notice that the only change in the negative is that it caused it to point in the same direction. So if one vector is pointing up in this direction, the negative vector will point the exact opposite direction. You could think about these as equal and opposite forces. One that's pulling against the other in order to create this equilibrium to where the object doesn't move. Now, in order to add vectors together, we're basically adding forces. We're combining multiple forces together to get something referred to as a resultant force. So if I want to define the resultant of two forces, namely vector A and vector B, then what I would simply do is I would start vector A and draw that until the terminal point. I would then pick up at the terminal point for vector B and add the new vector B onto the vector A. Wherever the initial point of A touches the terminal point of B, that is going to be referred to as the resultant of those two vectors. So in other words, in order to add vectors together, you just place one vector at the terminal point of the prior vector. Now we should realize that we technically could start by drawing B we could start by drawing B in this way, and then draw A in this way. And notice that that would also end at A plus B. So that would still be vector B plus vector A. So this is just demonstrating that with vectors, the commutative property applies. We could add two vectors in any direction, and it's going to give us the resultant vector. This is a demonstration of what we refer to as the parallelogram law. So we could see that if we started by adding vector A plus vector B, where this is vector B, that's going to be the same thing as if I started by taking vector B and adding onto it vector A. And so A plus B and B plus A are exactly the same. Now there's some very interesting properties that are going to help us with some trigonometric applications involving vectors, some very important properties of parallelograms. You should first of all notice that both of these vectors B are parallel to each other. And both vectors A, since they're the same vector, are also parallel to each other. So because of that, that means that alternate interior angles are going to apply. So that means that this angle here, let's call that maybe angle X, will be equal to this angle right up here, which is also X. And we could see that the angle over here, if we label this angle as vector Y, then we'd know that this angle is also vector Y. But keep in mind that we actually have two separate triangles technically here. We've got this triangle and the exact same triangle up here, because both of them have the angles of X and Y. So that must mean that the last angle is always going to be 180 degrees minus the sum of X plus Y. And so up here, that would be exactly the same quantity, 180 degrees minus the quantity of X and Y. So this is going to be a pretty helpful tool in order to be able to solve trigonometrically some applications involving vectors, because in order to do so, we're going to have to find some of those angles inside of the triangle. So in this example, let's just say that we have two forces, maybe two strings that people are pulling on that are trying to pull, let's say maybe it's a tugboat that's trying to pull a ship into harbor. And you've got two different boats, two tugboats that are pulling on this ship at different forces and in different directions. So it says here the two forces of 15 and 22 newtons act on a point in the plane. So let's just say that you've got this point in the XY plane. 15 and 22 newtons is nothing more than just a scalar. It's an amount of force. Now, particularly if we think about it in terms of the number of pounds that are being pulled, a newton is approximately 0.225 pounds. But what we're seeing here is that each of these vectors, this vector right here, is going to be shorter than the vector at 22 newtons right here, because the larger the magnitude, the longer the vector. It said the angle between the vectors is 100 degrees. So let's draw one vector in this direction here. There's one vector. Now let's say that that is a length, the magnitude of the vector is 22 units or 22 newtons. And now let's draw a 100-degree angle, which is a little more than 90. So there's 90. So 110 degrees would be something like this. Now notice that it's going to be shorter than the blue one because of the fact that it's 15 newtons. And so what we're trying to find is the magnitude of the resultant force. So if one of these vectors, let's call this vector u, then we can see that the magnitude of vector u is 15. And over here, this would show that the magnitude of vector v is 22 newtons. Okay, so those are scalars. And lastly, we see that the angle between is going to be 100 degrees. So we want to find the resultant force. So we always want to try to, as any problem, draw the resultant. So why don't we go ahead and start with the 22 Newton vector, and we're going to add the 15 Newton vector onto the tail end of it. So that should be parallel to the opposite side, and it should have the same length as the opposite side. Because if I can draw that new vector, which also shows that vector u is equal to 15 newtons, then I could see that the resultant will be this amount right here. So this is our resultant vector right here. Okay. So in order to find this resultant vector, we should realize that this is just the third side of a triangle now. Now, if we chose to, we could come up here, we could draw that last vector, okay, which is, by the parallelogram law, but we really only need to look at this one triangle, okay? And so if we look at this one triangle, okay, then that's what we're trying to solve. The problem is we have two sides of this triangle, but we have no angles inside. And so we can't use the law of sines or the law of cosines yet until we can find some more information. So the only information we have is the fact that the angle between the vectors is 100 degrees. So if we do draw that last side, we should recognize that this angle here, if we were to look at this angle, we could call this maybe angle A and this angle B, because notice it didn't cut the 100-degree angle directly in half. And if that's the case, then I know that this is angle B and this is also angle A. So one thing to recognize in a situation like this where we're given the angle between vectors but not the individual angles in the triangle is that angle A plus angle B is 100 degrees. So if angle A plus angle B is 120 degrees, and we now look at this triangle right down here, we should see that two of the angles of the triangle are angles A and B. So just like this angle here is 100 degrees, we also know that these two angles right here combine to give 100 degrees. So that means that there's only one angle left that this angle is allowed to be down here, and that's now 80 degrees. So we should see that we now have the length of a side of this triangle, the length of a side of this triangle, and an angle in between. What we really have here is side, angle, side. So since we're given side, angle, side, we're able to use the law of cosines in order to find the magnitude of u plus v. So let's use that law of cosines and write it out. We have the magnitude of u plus v squared is equal to the sum of the squares of the other two sides, so the magnitude of u squared plus the magnitude of v squared. Remember, magnitudes are just lengths, minus 2 times the magnitude of u times the magnitude of v times cosine of the angle between them. So this is just a matter at this point of plugging everything in. The magnitude of u is 15. So we've got 15 squared. Plus, now we've got the magnitude of v. The magnitude of v is 22 squared. Minus 2 times, and now we're just multiplying the magnitude of u times the magnitude of v. So the magnitude of u is 15. The magnitude of v is 22. And the last thing we've got is cosine of the angle between them. So we're taking cosine of 80 degrees. And so the law of cosines that we've learned previously is what's going to allow us to still work with vectors and answer some very similar questions. So let's go ahead and simplify this. This becomes 225. 22 squared is 484. And if we now work all of this out on our calculator, that becomes approximately 115 or so. So simplifying that gives me 594. But notice what that refers to. That's referring to the magnitude of u plus v. Or in other words, the magnitude of the resultant. So if I want the actual resultant, then that means that u plus v, the magnitude of u plus v, notice how I'm putting my arrows over the u and v, is equal to 24. And there's my answer. So notice that this is actually telling me that if I have a force that's pulling in one direction at 15 newtons, and a force that's pulling in another direction at 22 newtons, and I see that they're pulling at an angle of 100 degrees between them, then I know that the magnitude of the resultant force is 24 newtons. Now, in some applications, we deal with flight and bearing, and there are a few different vectors that act on a plane when it's in the air. So one thing is referred to as the airspeed. So let's just say that a plane has a particular airspeed designated by a vector. The reason it's so long is because of the fact that planes are going relatively fast. So let's say that a commercial airliner is going 500 miles per hour. Well, when you're that high in the atmosphere, there's also going to be wind that acts on you. So let's say that a wind was pushing you in a certain direction. The wind was blowing in this direction. This would be referred to as our wind speed. So you could probably see that if I'm trying to fly in this direction here, but the wind is pushing me in this direction here, then it means that I'm actually going to be ending going in this direction here. And this is referred to as the ground speed, because if someone was on the ground looking up at the plane flying, this is the direction that it would appear that the plane is actually flying in. So in applications involving airspeed and wind speed, we just have to recognize that we are in fact adding vectors together. We're adding the vector for airspeed plus the vector for wind speed, which is pointing in a certain direction. And when we do so, we have the vector for ground speed. So in these types of applications, the most important part of the problem is drawing an accurate diagram. And that's not the first time that's not the first time we've recognized that accurate pictures in trigonometry are what are going to help us to solve problems. But first of all, it says that an airplane that is following a bearing of 239 degrees. So the first thing to recognize is that in order to go at an angle of 239 degrees, or a bearing, we need to remember that bearing is always pointing from north and rotating clockwise. So that's a bearing of 90 degrees, 180 degrees, and a little bit more. So notice that this bearing is actually going to be pointing in this direction. Now it says it's an airspeed of 425 miles per hour. So I'm going to just label this as 425 miles per hour. Now, even though the vector is not 425, the vector is actually the direction and the speed, okay? But most importantly, right now, we just had to draw it in the right direction. Okay, so it says that it encounters a wind blowing at 36 miles per hour from a direction of 115 degrees. Okay, so it encounters a wind. So somewhere over here now, we've got another coordinate system. So it says it's blowing from a bearing of 115 degrees. So let's think where that is. That's 90 degrees is here and a little bit more. So this right here is the angle of 115 degrees. But it's blowing from that direction. So it's blowing at 36 miles per hour from a direction of 115 degrees, which means that we have this vector pointing up in this direction. Now notice that that's going to be shorter, but just so that we can actually fill this all in, I'm going to call this 36 right here. Now this obviously is not drawn to scale because 425 miles per hour is much more than 36 miles per hour. So that blue vector would typically be much smaller, but I want to be able to get a relatively decent picture here, okay? And so now the last thing it says is find the resulting bearing and ground speed of the plane. So let's see if we could recognize what that means. That means that we need to find out what is the resulting ground speed and bearing of the plane. We'll now take our time drawing these different angles. So I know that this bearing is a total of 239 degrees. But notice that by the time it's traveled halfway, it's already gone 180 degrees. So that implies that the only angle left, which is right down here, is an extra 59 degrees. Now notice that's really helpful because of this fact right here. This north-south line is parallel to this north-south line. And so that must imply that alternate interior angles are equal. So this angle right inside here formed between the north-south line and the purple vector is also 59 degrees. So that's already giving me part of the angle inside of my triangle. And I know that that's what I need because I have two sides of my triangle, but no angles. And I'm trying to find this third side, so I obviously am going to need to use the law of sines or the law of cosines. And so in order to do so, I need to have an angle. And so now let's take a look at the fact that this whole angle is 115 degrees. So that means that this little angle right down here, since the first quadrant is 90 degrees, this must be an additional 25 degrees. Okay. But if that's 25 degrees, then that means that by the vertical angles here, this is also 25 degrees. Here's 36 for a minute, so this is 25 degrees as well. And if I take that away from 90 degrees, that means that this additional amount is going to be 65 degrees. And so notice that we actually have that full angle now. Okay, the full angle is 65 degrees plus 59 degrees, which is a total of 124 degrees. So let's think back to what we're actually trying to find. Okay, so we're trying to find the resulting bearing, which really means that we need to recognize that if this piece right here is 239 degrees, that we're trying to find out what is the additional amount that needs to be or the additional angle that we need to turn through in order to get to the correct bearing. And so we're trying to find that, so let's call that theta. We're also trying to find the missing side over here. So let's refer to that as the resultant, or maybe vector r. So now that we see our triangle, we see that we're given side, angle, side, which implies again that we could use the law of cosines in order to find the missing side. So let's see that the magnitude of r squared is equal to the sum of the other two sides squared, so 36 squared plus 425 squared, minus 2 times the product of those two sides, which is 2 times 36 times 425, times cosine of the angle between them, which is 100, I'm sorry, that should be 124 degrees, not 25 degrees. So 124 degrees. And there we go. So notice if we were to work through that on our calculator, we would find out that all of this, and I encourage you to type that into your calculator to make sure you know how to do so. That means that the magnitude of r squared is equal to approximately 199,032, which means by taking the square root, we find out that the magnitude of vector r is equal to 446. Now let's think about what that means now. That's telling me the magnitude of that vector. Keep in mind that the magnitudes of these vectors were speeds. And so we now know that the magnitude of r is 446 miles per hour. So if you look at the diagram, that makes sense because notice that 425 degrees is how fast the plane's speedometer says it is. But the wind is pushing it along at that particular angle. So vector r is obviously going to be longer, and therefore we see that it's approximately 446 miles per hour. And we're still after the angle theta up here, which is just another angle inside of our triangle. And so notice that we should be able to use the law of sines now. Since I have all of the sides, I can actually say that sine of theta, which is the angle I'm trying to find, over its opposite side is equal to, well, now I also know the angle of 124 degrees, so I could say sine of 124 degrees over its opposite side, which is now the magnitude of r, or the resultant. So we can say that that is over 446. So by cross multiplying, we see that sine theta is equal to 36 times sine of 124 degrees over 446. Okay. Well, notice that when we calculate that, again, on our calculator, we can work that out. So sine, make sure that we're in degrees up here. So 124, take the sine of that angle, multiply it by 36, divide that by 446, and we get this decimal, 0.0669. So notice that that is sine of the angle, but we need to make sure, so what that implies here, and we can write that out. This implies that sine of the angle is equal to 0.0669. 0.0669. Which means we still have to take the inverse of that in order to find what the angle is. So the angle, if I take sine inverse, is 3.84 degrees. So we see that the angle is approximately 3.84 degrees. Okay. So we're ready now to recognize that if this angle up here is 3.84 degrees, that just means that the 239 degree angle added an extra 3.84 degrees. So if we see that again, that just demonstrates that that additional angle, the bearing, okay, is simply 239 degrees plus the additional amount of 3.84 degrees. Okay, which means that my final bearing is approximately 242.84 degrees. So there's our bearing. This up here is our ground speed. And again, even though we use the law of cosines and the law of sines in order to solve this, we need to realize that the most important part was our accurate diagram.